Oops. Okay, good morning, everybody. And thank you so much to be here the last day at 8:30. I really appreciate it. Whoops.
Good morning, teacher.
Now that shows lots of pictures of, so it's important that it's a little bit dark.
Okay, so I hope that the importance of volatiles in the formation of magmatic sulfide ores will wake you up. So first of all, why should we care about volatiles in magmatic sulfide ores if the parent magmas at the origin of this magmatic system is generally volatile pool? So we should care because even if the magma is initially volatile poor, magma ascent and crystallization can lead to the formation of a fluid phase at a relatively late magmatic stage. And more importantly, much important amounts of volatiles, external volatiles, can be supplied to the magma by the interaction with volatile-rich host rocks. And this could happen even at relatively early magmatic stages. So indeed, we do know that the interaction with sulfur-rich host rocks is considered as instrumental in the formation of several major nickel, copper, PG magmatic sulfide ores. So I'm not simply speaking about assimilation. So if you deal with carbonaceous rocks, the devolatilization of these rocks can produce abundant fluids that are carbon, hydrogen, and sulfur-rich, reduced fluids that can help indeed the saturation, to reach the saturation in sulfides. So the best documented case of volatile-rich or bearing intrusions is Norris-Talnach intrusion in polar Siberia. They are emplaced within coal-bearing sediments of the Tunguskaya series, or otherwise within Devonian argillites. And the interaction of the magma with these organic matter-rich rocks is producing abundant fluids that are coexisting with the magma. So just after me, Steve will speak about this intrusion much more in detail. So I won't say a lot about that, but just let me say a few words about the evidence, important evidence we have in these intrusions of fluid and volatile enrichment around the intrusion. So this is due to the occurrence of metamorphic and metasomatic aureoles that are extremely thick, and the intrusion breccia that are also very thick. And there is also important evidence of volatiles within the intrusions. So the occurrence of hydrous minerals and the occurrence of these taxitic rocks that are very complex rocks with variable textures and variable compositions. And they have some signature of magmatic breccia. And so within these taxitic rocks, we find, and within the picritic rocks as well, that are ore bearing at the base of the intrusion, we find these spherical textures that, as you can see here, they are voids in the primocrest framework. And so they are interpreted, and of course, they are associated with sulfide minerals, and they are interpreted as segregation vesicles. So old bubbles that are now filled with secondary phases. So I'm going to tell you why this association between the fluid phase and the sulfide melt could be important for the formation of ore formation at no risk, but not only. So this association has been longly known from metallurgical studies and has been applied for the first time by Margaux and co-authors in 2015 to magmatic sulfides. So they called a compound drops, these sulfide droplets, as attached to a fluid bubble. So I prefer the friendly name given by Steve, that is Drobble, because I find it much easier to remember. So I will use it for the rest of the presentation. So Margaux and co-authors, they propose that Drobbles can allow the upward transfer of the sulfide melt when the total density of the Drobble is lower than the density of the silicate melt. And so this floating is enhanced by sulfur degassing from the sulfide to the fluid phase. We perform both isobaric and decompressed experiments, and we noticed that the amount of sulfide melt is inversely related to the amount of fluid phase. And that's because sulfur is mainly a volatile element, and it prefers to go to the fluid. So depending on the proportion of fluid phase, drawballs may have different implications. So when the proportion of fluid phase is low, here for instance, the amount of the consumption of the sulfide melt is negligible, and drawballs may favor the coalescence of the sulfide droplets. Sulfide droplets that are attached to the same bubble. As you can see here in these microcity renderings of synthetic experimental drawball. So you see that each bubble can carry several droplets, and these droplets can easily coalesce and therefore accumulate the sulfide melt. And that's what we can observe in this BSE image of a whole experimental sample within its platinum capsule. You see that the sulfide accumulation are larger and more concentrated in the upper part of the capsule than in the rest of the sample. So we can easily imagine that the drawballs ascended through the silicate melt toward the top of the sample. So we propose that this mechanism could account for ovoid or globular textures that are observed in natural sulfides, with diameters ranging from hundreds of microns to several centimeters. You have a few examples here. Of course, no risk. These rocks that they also contain segregation vesicles, but also some other examples from komatiite hosted deposits in Australia or in Canada. You see particularly here nicely these globular textures, globular sulfides within a matrix of disseminated sulfides. So we also propose that the accumulation of sunk drawballs may contribute to the formation of massive sulfides. Once again, an example from no risk. And this could represent a solution to the unsolved problem of why sulfide droplets are deposited in a flowing magma, because we know from analog experiments and fluid dynamic modeling that the droplets during the flowing of the magma, they break up and do not coalesce, as we can see here in this simulation by Robertson et al. Okay, when the proportion of fluid phase is higher, sulfide melt is consumed by sulfur degassing to the fluid, and this is concentrating metals in the sulfide melt, and of course increasing ore tenors. You can see here the copper and nickel contents in the sulfide melt versus the amount of sulfide melt in our experiments. And you see that when the amount of sulfide melt decreases, so the degassing increases, both copper and nickel contents, they increase. You can also see that the experimental points, they follow the theoretical prediction by Campbell and Aldrich, they are factor law. And this prediction only consider the partitioning between the sulfide melt and the silicate melt. So this suggests that the amount of copper and nickel that goes to the fluid is negligible with respect to the amount of nickel and copper that goes to the sulfide melt. So finally, we observe that when the proportion of fluid phase is extremely high, we can have a total consumption of the sulfide melt and the crystallization of platinum group minerals. So for instance, in this experiment here, that's the one with the highest proportion of fluid phase, we observe these corroded sulfide blebs with zone areas that are richer in platinum and palladium. You have one example here and another example here. And we also observe this platinum-rich phase at the contact between the olivine and the silicate melt. And so this suggests that platinum group minerals may crystallize also at high temperature by desulfurization of the sulfide melt, and not only from the most evolved residual sulfide melt as classically considered after the segregation of the monosulfide solid solution and intermediate solid solution. So this mechanism is very similar to what was proposed by Sisson in 2003 to explain native gold nuggets in Hawaiian basanite. So he proposed that the desulfurization of the sulfide melt could lead to the formation of these gold nuggets here. So we also proposed that the mechanism could explain the formation of no-risk low sulfide IPG ores, that they also have these spherical textures that this time are associated with much low sulfide contents, as you can see here, but much higher PG contents. And so I'm very happy that also Ivan and his co-authors, they adopted this model for the formation, to explain the formation of this low sulfide IPG ores in no-risk. So if we look at the distribution of the ore types within no-risk Tannak intrusions, we see that the massive sulfides are at the base of the intrusion or even within the metasedimentary host rocks. The globular sulfides are in the lower part of the intrusion, and the low sulfide PG ores are in the upper part of the intrusion. And this is consistent with the involvement of an increasing amount of fluid phase from the base to the top of the intrusion. So a decreasing amount of sulfide melt and an increasing metal enrichment of the sulfide melt. So we propose indeed that massive sulfides represent sunk drobles. Globular sulfides represent floating drobles that are frozen in place. And finally, low sulfide PG ores may represent extensively degassed drobles. So several other magmatic sulfide ores are likely to be concerned because silicate-filled cavities are observed also in komatiite host deposits associated with sulfide blebs, as you can see here in Canada or in Australia. And as I told you before, the interaction with sulfur-bearing host rock is one of the most invoked processes in the formation of magmatic sulfide ores, at least for nickel-copper deposits. Okay, so to sum up, why drobles are important? They are important because the sulfide melt is consumed by degassing to the fluid, and this increases our tenors. They are important because for low proportional fluid phase, they favor the coalescence of the sulfide droplets and therefore the accumulation of the sulfide melt. And finally, they are important for extremely high proportional fluid phase. They may allow the crystallization of platinum group minerals at high temperature by desulfurization of the sulfide melt. So thank you for your attention. And here is the paper that was published last year if you need more details.
Thank you very much. Really nice presentation. I'm super happy to see those experiments. What do you think the volatile phase is?
I mean, for the moment, we did a look at the volatile phase variable composition. We do think could be important. But for the moment, what seems to be important is the amount of volatile phase. You see here that's really, there's a little bit of scatter because there are experiments with only water and some other experiments with water and chlorine. So there's a little bit of scatter in this trend, but you see that the main trend depends on the amount. So of course, the composition of the fluid phase should change. Okay? So in no-risk intrusion is probably very reduced because the interaction is with organic matter-rich rocks. In every deposit could be different.
Thank you.
Sorry. So what happens when MSS crystallizes from a drobble? Is it possible for then the bubble to take the copper liquid away and sort of physically separate? Is that physically possible? And is that maybe a way of, you know, physically fractionating copper sulfides from nickel sulfides on a deposit scale? And what I'm thinking of, Steve, here is, you know, those macrodike ones with the caps that we had, that was pure ISS.
I mean, what you generally observe that the ISS is the upper part.
Yeah, in those ones, yeah, but could it be possible if the bubble's big enough to pull that copper liquid away? I don't know.
Yeah, maybe not. We should ask Yao, because he calculated how this stuff can travel within a magma. And so, yeah, I think he did this calculation only for sulfide melt, but maybe if you add MSS and
Yeah.
residual sulfide melt, could be possible to simulate that.
That'd be interesting to see whether you could actually
I mean,
do that physical separation.
I do think that the bubble is keeping the globular sulfides in place, because you see around that there are disseminated sulfides. So I think that the difference between this one and this one, so Margaux, she's found that it's exactly the same. So why do we have these big globules? Because there's a bubble that is keeping them round, nice and round.
I have to just move on. Sorry. Yeah. So next we have Giada talk by Steam Farms about tribute to his work and that new concept in the real
Oh, thank you very much, everyone. Great to see you all here early on the last day of the conference. Actually, just before I start, I'll just add a comment to what Giada just said there. I think the bubble is essential to actually that differentiation of the sulfide droplet, because there's no reason why you'd expect that copper-rich liquid to be at the top of these things. It's actually denser than the MSS. If it was just gravity, it would be sitting at the bottom. It's the fact that it's the segregation vesicle mechanism is what keeps the copper-rich liquid at the top, we think. So anyway, okay, right. I need to, yes. Marta, we need you. All right, yep.